So my name is Amedeo Perazzo. I used to be the controls and data system lead for LCLS, which is this X-ray free electron laser that we've been running at SLAC since 2008. So a lot of this presentation is about LCLS. There are some parts of this presentation that I was given from the material science department head in LCLS. So I'm not an expert in material science, so you can ask any question you want, but I will refer to somebody else. After the initial week of this long program, we thought that there were some areas that we missed originally in the description of the complex workflows within the long program. And so we decided to add 3 areas. One is flux. We invited James Corbett from Livermore to talk about flux. I think it's going to be towards the end of the week, Thursday or Friday. The other area that we added was Legion, and we invited Alex Aiken and Seshu from Stanford and SLAC to talk about Legion. And then there was a third piece, which is what I will talk about this morning, which is this idea of a digital twin. The digital twin means different things to different people, but the way that I will look at it in this presentation is as a way to aid an experiment using simulations. And really using this simulation in real time, so as the experiment is happening. And this is something that is really ramping up right now. The fact that we now have relatively easy access to petascale and exascale computing finally makes this idea of running simulation in real time, driven by the experiment, something that can actually be implemented. So the arguments that I will talk about in this presentation is, one is an introduction to the LCLS, the free electron laser. We'll talk very briefly about the accelerator, the instruments, and the specification of the beam. This is the part that I inherited from the material science expert at LCLS. Then we will talk about complex workflows for experimental data and how we interface the LCLS beamlines to a supercomputer, which is something that Debbie will talk way more extensively later on this morning. And then this introduction to the digital twin approach. Even if the examples that I will give that we are working on right now are not material science related, I really hope that we can start having engagement on material science experiments soon. Okay, so now it works. So the LCLS, around 2008, SLAC stopped operating the electron-positron collider that started a decade earlier. And we readapted the last third of a Linux, so about 1 kilometer, to generate electrons, and then go through an undulator that generate the X-ray through a process called SASI. If at the end of the presentation we have more time, I will show a video that displays how we go from the cathode to the generation of the X-ray. Then eventually the X-ray reach the near experimental hole where we have some soft X-ray experiment, and then we propagate the X-ray to the far experimental hole where we have an additional set of hard X-ray experiments. So we have been operating now LCLS at SLAC for about 15 years, and we already have had significant impact on many areas of science, including resolving the structure of protein complexes that were previously inaccessible. one of the things that LCLS is particularly proud is this idea of making molecular movies, showing how chemical reactions evolve over time. Another area is the behavior of atoms and molecules in the presence of strong fields and probing extreme states of matter. This is the matter in extreme condition experiments where we use an optical laser to excite a material before the X-ray comes through and take a snapshot. So there are a lot of numbers here, but the ones that I wanted to point out are, first of all, the photon energy range. So in the soft X-ray experiment, we can go from 200 eV to 5 keV, while on the hard X-ray side, we go from 1 keV to up to 24, 25 keV. But one of the most interesting parameters of the LCLS really is the pulse duration. An X-ray FEL can generate pulses in the order of a few femtoseconds. Here shows 10 to 50, but if you ask nicely, you can get as low as 5 femtoseconds. The other parameter that I wanted to show is the repetition rate. We are right now commissioning a major upgrade of LCLS, which is LCLS2, which is a superconducting accelerator, where we will go from the 120 pulse per second that we have today to 1 megahertz. This is what we will start with, but the LCLS2 really is designed to generate 1 million pulses per second. So we have a significant data challenge in front of us as we deploy the LCLS2 now and the LCLS2 high energy upgrade in 2026. So the way to look at an FEL is like the flash of a strobe camera, which then allows you to create stop action movies of atoms and molecules. One of the techniques that we have used extensively at LCLS is this diffraction before destruction idea, where the X-ray comes and illuminates the sample, nanocrystal, and molecule, and will destroy this sample. But the diffraction process is fast enough that we can take a picture of the sample before the destruction happens. The way to look at LCLS from a data perspective is using the data system as a lens into a process, into a molecule. Because really, since most of the times what we get are diffraction images, we need to go back in real space, and that's where really computing plays a key role in making the LCLS successful. This is an example of what you can do with nanocrystallography as you increase your computational complexity from terascale to petascale to exascale. So not only you can analyze more diffraction patterns, but you can also increase the analytical detail and the scientific payoff as you introduce more complex algorithms. And the first example of digital twin that I will show in this presentation is indeed this X-ray tracing idea, where we use a simulation to increase the accuracy of the phasing process. And will also, we believe at least right now, will allow us to do nanocrystallography reconstruction with a smaller number of events. So this is the part that I inherited from Apurva Mehta, who is the LCLS department head for material science. One of the scientific trusts where really LCLS can make the difference in material science is the idea of using X-ray techniques to study short-lived excited states. The way that we do this is by illuminating the sample before the X-ray arrives to take the snapshot with an optical laser. And then we measure the time between the arrival of the laser and the arrival of the X-ray laser. And this allows us to study the evolution of the excited states using spectroscopic technique, inelastic X-ray scattering, X-ray emission and absorption spectroscopy. And we can easily study changes in material morphology and defects. The example that I will show in the next 3 slides are magnon dynamics in cuprates, laser ablation, and metal additive manufacturing improvements. So SCLS has this advantage where we can reveal the interaction among the fundamental quasi-particle and collective excitation of solids with far more precision than has been previously possible. So this one are some results from a study that was made to understand the origin and stabilization of a striped phase for the lanthanum barium copper oxide. SCLS is also in an ideal position to study this phase space of the laser fluence versus the pulse duration of a laser during a laser ablation experiment. This is an example of an experiment where they were changing the pulse duration of the optical laser in the tens to hundreds of picoseconds, and they were able to show how low Q you can see particle formation. This is you see as the pulse duration changes, you can see the different features that appear on the diffraction pattern from the X-ray laser at small angle scattering. And here you can see the changes in crystallinity at high Q. And then you will see that, you see when there is this very clear ring, this is where a gold crystal was formed. Another area where SCLS has been able to make a difference is the hierarchy of timescale in metal additive manufacturing, from solid mechanics, solid state transformation, thermal fluid dynamics, and particle dynamics. The thing that I wanted to point out is some excerpts from this impact assessment report on theory simulation in condensed matter, which is very recent effort, a few months ago. And you can see how the merging of simulation with experiment is really playing an increasingly important role in what we do with material science experiment at free electron laser. This committee mentions strategies for comparing theory with vast arrays of experimental data, use molecular dynamics to inform the design of experiments before they are performed, and encouraging the community to put considerable effort to create code specifically designed for XFEL matter interaction. And then they observed how ionization threshold at energies that are different from standard theory has led to many groups now employing density functional theory to attempt to understand matter under extreme conditions. So at NFEL, we have roughly of the order of 20 plus different scientific workflows, each one with different requirements, each one being applied in a different instrument. Here, we tried to indicate the computing requirements for different experimental technique. You can see how the highest flop requirements are for the analysis of inverse problem, like single particle imaging. The lowest is for coincidence and nonlinear spectroscopy. But one thing that is really becoming clear is that there are different areas, like nanocrystallography, where we believe that by increasing the computing capabilities, we will be able to perform better experiments. And there is a little bit more later on about this idea for nanocrystallography. So this is an example of the kind of information that we need to process when we run an experiment at FEL. There is the accelerator diagnostic aspect, where we need to be able to optimize and characterize both the electron beam and the X-ray beam that is coming to the hatches. Then there is a high frame rate detector, where we need to build detectors that are able to sustain the pulse rate that will be generated at SLS2 and SLS2 HE. We need to be able to reduce the data on the fly using edge computing capabilities, because really, in the end, the content, the science content of the data that we take can be dramatically reduced through various techniques. But things like vetoing, where we throw away the images where the X-ray didn't hit the sample, or where the X-ray hit more than one sample at the time. And we let go through only the good hits where the X-ray illuminated one sample. Or we can do things like feature extraction, where we go through the diffraction images and we pull out only the information that we really care about, like the list of the Bragg peaks. And then, of course, we do things like lossless and lossy compression. We need to be able to provide to the experimentals fast feedback in real time of how the experiment is going. And then eventually we need to be able to do the reconstruction stage, where we can build the electron density of a macromolecule, or do a molecular movie of a chemical reaction. So the way that we do this physically is we built a data reduction pipeline where we move these multiple terabyte per second data streams coming from the detectors. We can use the data reduction pipeline also to provide sub-second real-time information to the users as they are taking data. And then we move the reduced data to a fast feedback storage layer where we can get a few minutes feedback on how the experiment is performing. And then eventually we move the data for computing over the next weeks or months or years, both on-site for a petascale experiment, or off-site to NERSC and the leadership class facility for experiments that have more computing intensive requirement. But now, one of the things that we are really pushing hard is try to use this layer also for real-time behavior, and that's where really things becomes interesting. So this is an idea of complex workflow. This has nothing to do with the complex workflows that this community is used to. These are really for data analysis. I will not stay here too long because I don't think it may be too interesting for a bunch of aspects. The only thing that I wanted to point out is that the focus of these workflows is to provide an automatic path for the data to move, for the jobs to run, where the users have very specific places where to drop the intelligence that they want to apply to the experiment. So in this case, all the users need to do is to provide the last mile algorithm, and then we plug it into a framework that handles all the parallelism. and that handle the submission of the jobs. And then the other piece that we need to provide is this airflow DAG, where fundamentally is a simple Python script that decides, that defines what are the executables that need to run and in which order. And then we kind of take care of everything else. We use the SuperFacility API that Debbie will talk more later today to interface from this automated run processing box to the remote over the network, over the ESNet piece. We then submit the job in quasi-real-time. This is something that will need more attention in the future because the real-time behavior is not there yet. And then we provide the science data and results back to the beamlines where the user can use the electronic logbook to see automatically the results of their jobs that was triggered whenever an event finally shows up on the supercomputer. So this is a very different complex workflows. On the other hand, there are some parts here, like the SuperFacility API, that really can be used by also the simulation workflows that this community is interested in. So then this part of the presentation is about this idea of a digital twin approach, which at least here is defined as integrating simulation with experiments in real time. So up to now, there isn't really been much attention to simulations. I come from my energy physics where you don't do anything until you have a decent enough simulation that will tell you how the experiment will behave. In light sources, simulations are not a thing, at least up to now. But as facilities become mature, the experimental repetition rate goes up. There is this sense that it will be critical to know about experiments better before, during, and after the experiment happens. And so you can tell also from the slides that I showed before about the recommendation from the impact assessment, how simulations will play a much more critical role in the future to predict the behavior in your experiment, steer the experiment in real time, and build smarter and faster experiment. We will do this by interpreting experimental data, like in the first example that I will show for X-ray tracing, training machine learning algorithm to determine corrections and calibration, and prototyping novel accelerator operation modes, and also optimize the accelerator, which is the second example of a digital twin that I will show. But there are challenges of using a digital twin. The first one, of course, is that the computing requirement that I showed before in the slides that were in teraflop for most spectroscopy experiments and in the petascale for inverse problems, we really diverge once we start applying this digital twin. On the other hand, having petascale or exascale access in the future will be much easier than it is being up to now. In addition, there is a timescale challenge. To tune the accelerator, you need to be able to bring in millions of process variables in real time to understand how the accelerator is behaving and how the accelerator is responding to change in parameters. So this massive data throughput and real-time aspect will be the first challenges that we need to tackle. Second challenge, phase space. You need to make the right experimental data available to the simulation and vice versa. On the other hand, being able to use simulations will reduce the phase space of the simulation itself and vice versa. By using a simulation, we'll be able to have a better idea, for example, of where to scan for parameters. And so we will be able, through this interaction, to reduce the phase space that is required by the experiment and the simulation, and the computational cost that I already mentioned. So the first example of digital twin is this idea of using simulation to aid the convergence and resolution in nanocrystallography reconstruction. The science goal is to enable a reconstruction of a time domain movie of enzymatic reaction. The experiment that we are really focusing on is the photosystem II protein complex. And the idea is to use this new X-ray tracing approach, where we try to apply this LBFGS optimizer to estimate structural parameters from diffraction data. The idea is that, so these are the zoom in of the Bragg peaks that you can see on a detector at an FEL in a nanocrystallography experiment. And you can see that each Bragg peak really has a structure. And up to now, what we have been doing is to sum up all the information inside the Bragg peak and get one number, which is the intensity of the Bragg peak. But really what it turns out is that if you use the information within the Bragg peaks, you are then able to resolve the polychromatic aspect of the X-ray, because really the X-ray has a spectrum, energy spectrum, that is non-trivial. And also you are able to handle the imperfections in the crystal, and this eventually will give you a reconstruction that is faster, it has higher resolution, and doesn't need as many images. So the idea is that you have standard nanocrystallography reconstruction where you integrate the Bragg peaks into one number, and then create the protein structure modeling through these Miller points. And what we are adding right now is this piece here on the right, which is the digital twin approach, where we use a mechanism to model the crystal orientation and the structure factor. It turns out that at an X-ray FEL, you can factorize the intensity of the Bragg peaks, like this one, in three components. One is the spectrum of the incoming X-ray beam. One is the crystal orientation, and the other one is the structure factors. And so once you have this factorization, then it's relatively straightforward to optimize each one of these components individually. The spectrum comes from the diagnostic of a machine. Every event will have a spectrum associated with it. And then we use this diff Bragg code to model the crystal orientation, because every time that the nanocrystal is illuminated, it can be in any random orientation. And this step here will allow you to calculate exactly what was the orientation at this point through this optimization step. And then you do the same thing for the structure factors, and if you want to spend a little bit more cycle, you repeat this once more. And so this is work in progress. We hope to have something working by the end of the year. But right now, we already have an indication that we are able to provide better details than just summing up the Bragg peaks, and we can do so with less events. The second example of a digital twin is the accelerator optimization. There is a group that is building this start-to-end simulation for FEL called Lume that is trying to answer to this question. How should the accelerator be optimized to provide the best pulses? When an experimental group comes in, typically they will say, I want this pulse length parameter, this energy. And the ability to provide those parameters has always been kind of an art at the accelerator. People will change parameters manually on the machine and see how the energy, the pulse length respond to this optimization. And so being able to do this through a digital twin where you have a model of how the machine will respond, and you provide real-time information about what you are changing and what you are measuring, has the potential of dramatically improving the way that we optimize the machine for providing the best pulses. This Lume is also trying to see how realistic pulses propagate through the instrument and interact with the optics, how the X-ray pulse interact with the sample, and what is the impact of detector performance on the diffraction images, and things, kind of fundamental, like how much data do I need for a successful experiment. So right now, the role that I'm playing in this effort is very technical. My job is to make sure that we can propagate in real time these millions of process variable information from the machine to the operator, and then provide a mechanism to create pipelines where this information is simulated, compared to the experiment, and then provide the results. But there is very good indication that we will be able to provide much better optimization of a machine, starting even from model-free optimization using machine learning algorithms to find the best parameter sets, through more complex models like Bayesian optimization, and eventually being able to provide models that assume a good understanding of how the machine operates. So the strategy right now is to start with very simple, efficient methods, model-free, and then as we learn more about how to simulate the machine, move more towards a digital twin approach. So this is the conclusion of this presentation. As FEL science is getting more mature, making good use of beam time is becoming critical for both the facility and the users. If we become more efficient in making experiments, we'll be able to run more experiments, which will eventually provide more science to the community. We now know that simulation can optimize data taking by reducing the time needed to acquire scientific results and improve the quality of data collection itself. We are working on better reconstruction algorithms. We are now able to provide better sampling strategies that are less random. We are getting better at identifying sources of errors between the simulation and the measurement. So the key message of this presentation is that if you have ideas of possible engagement with LCLS, please reach out. This push for putting simulations together with experiment will only intensify over the next few years. And so I think that creating a stronger connection between the experiments and this community will be fundamental. I have one other slide, but depends on how we are doing with time. So this is a relatively old video of how a free electron laser works. This is what we call the gallery, which is on top of the accelerator itself. This is the laser that generates the ultraviolet light that eventually hits the cathode. This is how we generate the electron pulses. Right now, this is 120 pulses per second. This will become 1 million pulses per second as we go to SLS2. The electron pulses then go into the accelerator itself. Right now, it's the last kilometer of a LINAC, where these pulses will reach of the order of 8 GeV. This is along the accelerator itself, there are both diagnostic and optimization benches. Like this is a bunch compressor where they reduce the size of the electron pulse itself. So this is the 1 kilometer of acceleration. This is another bench compressor. This is the second chicane. And then the electron pulses move through a bunch of diagnostic elements that do things like measuring the energy of the beam, the position of the beam. And this is all information that then we collect from the machine and save together with the science data so that the users can make the best interpretation of their data based on what we were doing, what these pulses were doing in the accelerator itself. So this is just a beam transport tunnel before the pulses reach really the core of an FEL, which is the undulator. The undulator is what creates this SASE process where see, there are these electromagnetic fields that wiggle the electron pulses and start generating photons. Then these photons interact with the electron pulse itself, and through the SASE process, there is the creation of this resonance that generates this very collimated in energy, space, and time X-ray pulses. But here they try to represent with these light symbols. Eventually, at this point, the X-ray are still together with the electrons. The electrons get dropped through this magnetic field onto the ground. This is the dump, and only the X-ray keeps going to reach the instrument itself. Soft X-ray are relatively easy to redirect, and so there is the soft X-ray experimental hole, which is right after the undulator, where in a few meters you can redirect the X-ray entirely. And here there are now 4. This used to be 3. Now there are 4 hatches, which have very different specifications. Very different instrumentation depending on what kind of physics they are trying to do. And then there is this transport tunnel. Well, let me show this one first. This is an example of sample injection. The molecule, the nanocrystal, is dumped on the beam, which destroyed the sample but takes these diffraction images. And then from these diffraction images, you can do the reconstruction of the sample at the time that it was illuminated. And yeah, so this is my presentation. With SLS2, the accelerator looks very different because there are these very huge cryo modules, which are superconducting components that will be installed in the first third of the LINAC, so the first kilometer of the LINAC instead of the last one like this one, and will be able to operate at 1 megahertz. The main challenges will be on the data system, where we have order of magnitudes more data than before, and on the ability to bring these cryo model set to 2 Kelvin. And just these two components really have made SELS2 a big enterprise.